Okay, hello everyone. Thank you for having me. Thank you for the introduction. Okay, so as you already heard, my name is Andreas Moser. I work at Google at the incident response team. But don't get confused, I'm not actually an incident responder. I'm a software engineer that write tools like GRR, the tool that I'm going to present today. A couple of months ago, we talked to one of the guys that helped organizing this conference. Just a quick note, they're doing a great job actually. I like this conference a lot, awesome. And we were talking about GRR, and he was saying, you know what, why don't you just come and explain a bit what you guys are doing at Google, how you do forensics at scale. And yeah, here I am. This is what I'm going to do today. So, what is the challenges the Google IR team faces every day? So, let's say you have a computer, Joe saw something weird on his machine. You have to investigate that machine, but it's on the other side of the world, right? It's somewhere in a random country, not a good network connection, but you still have to do something about it. Happens all the time to us. Or you have to forensically acquire 25 machines for analysis, but apparently they're all not Windows, because at Google, Windows is not the most used operating system, I'd say. Or this third problem, which is maybe the most interesting one. You have one machine, and you find out that it's compromised. You find something weird on this machine, and then you want to check if in your fleet, and your fleet is big, let's say a number of 100,000 machines, you want to find out which other machines are compromised too. And a while back, the incident response team, they had to, when they tried to solve this problem, they had to evaluate the options that they had, and they were not content with any of them. They were not sufficient. So what we decided back then is that we would just roll our own, and this is how GRR came into play. So what is GRR? GRR stands for GRR Rapid Response. It's a recursive acronym like GNU, and it's an agent-based forensics investigation tool. So agent-based means that we have a very lightweight agent that we push out to machines that we want to investigate, that runs there, contacts our server back, and then the forensic analyst can just sit in front of his nice little user interface, click some buttons, and the investigation happens. This tool is fully open source, so you can just download this from the web and use it in your company. I'll show you later how this is maybe done. Google has committed to this project, so we decided that we will support this project long term. And at the moment, this is built, maintained, and used by Google, and also by other companies. So it's always hard to get the data from other companies, like what are they using, what the tools are, what the scale is. But we know that some companies are using this, some companies are evaluating GRR, and they start to contribute back. At Google, we have 4 full-time developers, one of them is me, and we have lots of other people contributing code, like the forensics analysts. When there is not so much to do, they contribute code to GRR as well. At the current stage, it's a tool built by engineers for engineers. So it's not a solution that you can install and click some buttons and everything will work. It will mostly work, probably, but this thing is really complicated, so there might be some breakage, and then you need someone who understands. But it's not that hard. On the project FAQ that we set up on our webpage, you can read a bit more about our motivation. Okay, so let's jump into GRR. So this diagram shows the architecture of the tool we built. It's very detailed because I stole it from one of my colleagues' presentations. I'm not going to go into the details today. I'm going to talk more about the capabilities we have. But what you should take away from this slide is that you have the clients, the machines that you want to investigate. They sit somewhere up on the right in the cloud, on the internet. Doesn't matter where they sit, as long as they can connect back to the server, you're good. And then stuff happens in the middle, magic stuff. And on the lower left, we have a little GUI console, a graphical user interface, and this is where the analyst sits. I will show you later how this looks like. This is the basic architecture of GRR. So a quick word on our clients. We need multi-platform support, so we have GRR clients for Windows, Mac, and Linux. They work very well. They are super stable, robust, and low impact. So how do we do this? They are written in Python. This is a very nice touch because they don't really crash. You can just catch any exception that comes in and carry on. We have done a lot of work that I'm not going to explain today. We have a research paper out that where you can read more about this stuff on our project page. But we have invested a lot of work into constraining the resource usage of the GRR clients. So there is memory, resource constraints, CPU constraints, everything. When you're sitting on a machine where GRR is running, you will not notice that it's there until the analyst does some really crazy stuff, right? So it's very low impact. We also have a watchdog process that restarts the clients all the time. The client itself, very lightweight. It doesn't contain any logic. So basically it has very simple functions: download this file, list this directory, stuff like that. And the actual logic is encoded in what we call flows on the server. So the flow is like a workflow. Let's say you want to get the Chrome history of some machine. Then the server knows, okay, the Chrome history, there is one per user, so it calls the client and says, give me all your usernames on this box. They come back, and then the server says, okay, for each of those users, try to get this directory username / Chrome history, whatever, right? And this has the advantage that we can easily update the logic, because the server is very easy to update. The client's not so easy when you have lots of them deployed. Okay, so and now I'm going to show you how you can use this tool as an analyst. So I'm going to show you a couple of screenshots about the graphical user interface that we have implemented. I'm very sorry that I don't do a real live demo, but I didn't trust the network here. So my files are always flaky. Yeah, I know. But there's an offer. If you want to see this live, I'm around today. You can just hit me up. I can show you a bit how this really works. So in your browser, you go to the admin UI that you have configured. You get this little search box. You type in, can you read that? Yeah. So you type in a host name or a username or a MAC address or whatever, and you get a result. So you see, okay, there's a little green light on the left. It says the client is online, and you get some details because you have to know that you're looking at the right clients. There might be like 10,000 in the database, right? So you don't want to do the forensics on the wrong machine. Right? Then you open it up, and you get a little overview, very basic information, the same thing essentially you've already seen in the search box. What's interesting here is on the right side, we have an age column. So each of the data points is timestamped. And whenever you get new information from the client, the old data is not overwritten, never. Right? It depends on the data, but usually the interesting data does not get overwritten. So what happens is, instead, it creates a new version. And when you look at client info on the left, it has a little plus above it. So that means there's more versions available. So you click on it, and you get the full history of the client, whatever you downloaded in the past. So this is how you can work with the client. So we have invented this thing called virtual file system. On the left, this is this tree. So this is a tree-like structure that maps certain client functions into branches of this tree. Sounds very complicated. It isn't really. So if you look at the screenshot, someone has opened FSOSC. That means the FS stands for file system. So it means you want to look at the file system on the client. And then you go into OS, which means you use the operating system API to get the files, and then see this is what you want to read, the disk, right? And you can see you got a directory listing already here. Someone downloaded the file, this root sector file up there, and you get a little hex view, so you can directly look at the files on the client in your GUI, right? So just download them, you can analyze them directly in the front end. What you also have is the SluiceKit integration. So the SluiceKit is a forensics tool that allows you to open raw disks and parse the contained data. Like, it understands NTFS, it understands multiple other file systems. So what you do is, instead, you go fs_tsk, which is the SluiceKit, and you get this raw volume. It's the same disk, the C column that you see above. It's the same disk, and you just open it in raw data and parse the data yourself. And then you can get this metadata that is usually hidden from you by the Windows API. So you can see there is a $MFT on there, and you can just download the MFT. Right? And this is very helpful because the operating system API in Windows doesn't let you open all the files. So when a process is running, for example, the file is locked and you can't get it, with this loose kit, you can get everything you want. Okay. So far, yeah. This is one thing I wanted to show. This is a screenshot that shows you the different flows we have. As you can see on the left, we're now in the flow tree, so there is lots of the flows, lots of them. There is find files, list directory, list processes, Chrome history, and then we have this thing called an artifact collector flow. So we have defined lots of artifacts. The artifacts are some data points that are interesting on the client. So for example, there is one selected, can't really read that I think, it's security event log EBTX. Right? So this artifact defines what a security event log is and where it resides on the client. So you just select this thing, you say I want this event log and fire it off, and the file comes back. You don't have to do anything else. 2 clicks, event log comes in. So this is how you can interact with a single client. So far, those features are not great, I think. They're cool, but they're not great. And there are many more. But today I want to focus on one thing that I think is really, really cool. And this is we provide live memory forensics on those clients. So how do we do this? GRR comes with memory acquisition drivers for all the operating systems that we support, Windows, Linux, and Mac. How it works is you take the driver, you put it in a signed blob, you fire it off to the client loads the driver for you. That works very well on Windows and Mac. On Linux it's a bit harder because you have to match the exact kernel version of the kernel that you're investigating. So we have a really cool project going on in November. What we're going to do is we're going to hack the driver before we load it, such that it just works on any client, on any kernel version without blue screening the box, I hope. We're almost there. We have code execution, we just have to put our driver in. I think this is really cool when this happens finally, but in the meantime you can just compile it for that machine. And yeah, Windows and Mac are not problematic at all. So what those drivers do, they give you a file handle. They give you a file handle that actually maps into the raw memory. So you open the file and you get raw memory contents. This is kind of like the old /dev mem that Linux had. And when you have this, then the great advantage is when you have a file, you can do normal GRR file operations on this memory file. So you can grab it, which is essentially a scan through memory. Or you can just click on download this file, and that essentially gives you a memory image from that box, right? So I'm sitting in front of my GUI, I click download image, and the machine in India gets image to my machine here, or to my server, right? And I can just download the image, work with it, whatever I want. So I'll show you how I did a grab. So I sent this client, this is my test box in Moser 0, and I searched for the string bad because I wanted to find the badness, you know? And I told it to give me 100 bytes before bad and after bad, and then it says on the right, I don't know if you can read it, it says not a TIFF file bad version. So it found the badness in memory. It's at 2 megabytes in a bit. Okay. So this is how you can look at this in your GUI. This comes directly from memory from some random machine somewhere else. Okay. Grabbing memory is kind of cool, but memory images give you way more information, right? You have the kernel structures in memory. You can parse out all the processes, everything. So this is way better having the memory image than just having a grab, right? But obtaining memory images is hard. That doesn't really scale because they're big. It's a lot of data. Essentially, what you want is a very little piece of information. Like you want to get just the processes, right? And then you have to download gigabytes of data. That's not feasible. So we had to do something else. We went a bit more creative. So there is this toolkit called the volatility framework. The volatility framework is a memory analysis framework that gives you exactly that. It takes a memory dump, reads it, and passes out all the information you need. So there is literally hundreds of plugins that give you, like I listed a couple here, a process list, a DLL list for the running processes. It scans for mutexes, or you have sophisticated plugins like nullfind, which parses kernel structures and looks for anomalies. And those anomalies might indicate malicious code running on this box, right? So what we have done is we use a modified version of that. There's Cadet branch. Cadet is one of the developers of GRR and contributors to volatility. And we have improved the performance of this and the stability. Not the stability of the tool itself, the tool is fine, but the stability of the parsing. Because what this allows us is, when we have our memory driver that gives you a file that points into the raw memory, we just can use volatility to tell it, this is your memory dump, and volatility will open the live memory, thinking it's a memory image, and operate on that, right? So this is what we've done. We ship the volatility with the client off to the machine we want to analyze, and then we can run volatility plugins directly live from memory. But here we need the stability improvements, right? Because it's, volatility doesn't know that it's operating on live memory, because who would ever do that? So it has a list, and it just goes through the list, right? Processes, for example, it just follows the pointers. But at some point, the operating system might go and kill one of those processes, and suddenly the pointers are dangling, and volatility doesn't really think about this case. So we had to improve the stability, but now this totally works. So what this allows me to is I go into my web interface, I select the client, I choose analyze memory, and I put in, let's say, PS list. Yep. Client goes off and pulls back the process list directly passed out from memory. Not via the operating system API that might be tampered with, but directly from memory. And then I get this nice little view in my browser. Or I can do a DLL list, kind of the same thing. The svc host.exe uses all those DLLs, just one click. Okay. But having one client to analyze is kind of cool already. So we use that. We have an incident, we just fire up GRR, we analyze this one client because it's so easy in the GUI, right? But what's really cool is we can do hunting now. So hunting means I have a flow, and I want to run this flow on all the clients in my fleet, right? Or on a subset of the clients. Think of all the Windows boxes, or all the boxes which have a host name that corresponds to some pattern, right? And now we can do two things. First, you can do fleet checks. So we can say, the problem that I stated in the beginning, I have one suspicious file on one machine, find me all the other machines that have this file too, right? It's very simple. Just do download file. This is the name, schedule it on all the machines, and whoever does not report an error, very suspicious, right? And what we also can do is we can do baselining. So we take a data point, let's say the run once registry keys, and we download them from all the machines. And then we do a little histogram. So we see, okay, this registry key happens to be on 100 boxes or 1,000 boxes, right? Then it's probably legit. But if I have one that's only on one single machine, then I should probably investigate that. And I can also do timelining. So I can just store the results every week, for example. And then I can see, okay, what new run keys are in my fleet compared to last week, right? So what's the performance of this? In the GUI, you can click on graph, and you get an output like this, with a little change. On the left, it has numbers usually, but this is the second biggest instance that we run at Google, and they don't really want to give out the numbers, so I had to remove them. But you can safely assume that this is more machines than what is feasible to analyze manually, right? This is a grab through memory, like searching for some signature of a malware in all the Windows machines. Right? And you can see, so the way it works is that the clients, they look for new hunts every half hour, once every half hour. So you see in the first half hour, all the clients that are active at that point, when I start the hunt, they get it in the first half hour. And then the rest of the clients that trickle in slowly, those are machines that are offline, right? This is like other time zones, people that went home, that come back in the morning, switch on their machine, first thing, GRR comes and checks the memory, right? So, but the takeaway is that in 24 hours and 5 clicks of a button, I can scan the whole fleet all the memory for this one signature, right? And yeah, I have a very high probability of finding a hit. Like this is about 2/3 in half an hour, right? So that's a pretty cool capability in my opinion. If you like this stuff, if you think this could be useful for you too, it's actually not that hard to set this up. So you've seen in the beginning there is lots of components of GRR, but we have a script that runs them all on one machine. So this is all you need. You need one Ubuntu server. You go to our homepage to getting started. There is a little installation script. You run the script. It asks you some very simple questions like what should the credentials be for the admin UI, how do you want to log in? Then you wait, and then the server is installed. You open the GUI, you download the clients that have the matching keys already. They can talk, you just run them on the box you want to analyze, and you're good. Right? You should put a developer in it and contribute back. If you do that, that would be really cool. The contribute part is optional, I think, but the developer probably you will need sooner or later. So it's, as I said, it's not a complete product. It's kind of beta software. It's kind of software for engineers, but the capabilities are well worth it. So if you do this effort, I think it will pay off for you in the long run. Okay, this is all I have. I hope there are some questions.
Is this application can be used to analyze in-memory only malware that doesn't leave the disk at all?
Yeah, of course. Yeah, you just need a signature for it. You just fire it off. The GRR client scans the memory. If it finds the matching string in there, you got it. Yeah. This is the big advantage of doing this, right? Because otherwise you have basically no chance.
What kind of precautions do you have to take to prevent the client itself from being misused if the machine is compromised, or the driver that accesses memory?
So the driver that accesses memory, it has the file handle that it creates. Yeah. Has permission set to system only, yeah. Right? Which is the same as GRR. So if you can open this file handle, then your system already, yeah. There's no point detection, right? Yeah. So misusing the client is kind of hard because we have a lot of encryption in place. So essentially what you would have to do is you would have to steal our private key, yeah. And then man in the middle with an open source server, which you could do, but you need the private key, otherwise the client won't talk to you, right?
Yeah, but that's true. Did you say the client was written in Python? Yeah. Or, okay, so what are the options for somebody to actually modify the client in situ, like on the box?
Modify?
Like if there was some malware that knew that you had...
Yeah, of course you can modify it, sure. I mean, but this is the thing, right? Once you have the malware on the box that has the same privilege as your forensics tool, yeah. Then you're kind of out of luck, right? So what we have in place for this, there is some minor obfuscation. Yeah. So it's not entirely obvious which process is GRR. You can give it your own name, you can modify some things. We are also thinking about doing some more obfuscation in like maybe next year, because we have the memory driver, we can enable write mode. Right? We don't do this. All that the GRR client does is read only, because write mode stuff is really dangerous. Right? But we can enable write mode, and then we can just unlink ourselves from the process list and stuff like that, right? Like malware techniques, right? But to fight malware is kind of okay, I guess, I don't know. Anyone else?
Do you have any tools in that do automatic checks, or is it very much comparison against a few other machines to see where the differences are?
So we do not have automatic checks. What we're starting to do now is we do periodic counts. So basically just lots of data collections, right? The problem that we have is kind of the analysis part. So the collection part, that works perfectly fine, right? So the GRR just works. But the problem is then you have this huge amount of data, right? And then what do you do with it, right? It's kind of an unsolved problem. At first we were like, oh, we download all the registry keys, and it will be cool, right? And then we look at them. But then you have like millions, and then after a while you get tired, right? When you look at them. Right? So we need to think about more intelligent analysis methods, right? So this is kind of the future work that we're going to do.
You mentioned the signature-based detections. Can you import application or use any other sources?
So we looked at IOCs. We started implementing some things, but then we stopped. I think it was just too complicated. But it's very simple to transform IOCs into a format that GRR understands, right? Because our format is really basic, right? What we do is what we are trying to do is GRR signatures, and then that covers a lot already, right? So you should always have GRR signatures. I think that's a sign. Okay, thank you.